Hello, here's Ms. Walsh, and today we're going to do day 3, okay? So we're going to find the derivative at a point with the calculator, and then we're also going to look at intervals of increase and decrease, okay? Skipping the starter. All right, so here it's asking us to find the derivative using the power rule. We did that last time, and then to use our calculator to confirm that the slope that at x being 2 is indeed what we find that it is. So remember the power rule is always, so take this down, so this is going to be 3 times 4x to the 4 minus 1. So this is going to be 12x to the 3. Remember what this is? This is the slope of the tangent to the function at all points, okay? So now if you need it at 2, then what you can do is you can just say, hey, I want the slope at 2, and we're just going to substitute the x value being 2. So what is this? This is 8 times 12, so this should be 96. Okay, if you want to confirm, then we're going to go to the calculator, and you can pause it, take a moment. I've already entered it in. And then what you're going to do is you're just going to go, hey, I'm going to go to 2, and now can you give me the slope? So you're going to go to function, you're going to go to slope, and ta-da, there it is. So what that actually means is that at 2, and you can see that there's a very big positive slope here. So our answer actually makes sense. Let's give ourselves a happy face, woohoo. Okay, you can try all the other ones. Again, take the power rule and then check it with the calculator. Remember, when you take the derivative, it's the slope of the tangent. So let's do the fourth one though, because for this one, so just a word about this. Since we cannot divide by 0, this is just something called a restriction. You don't have to worry about it. It just means that you will not have a value for this function at 0. Okay, so the first thing we have to do here is remember this is what we call to prep it. So the first thing is that remember, change floor, change sign. When you pull it out of the denominator, then that power becomes negative. This is not the derivative. This is just an equivalent form. So now let's derive. Let us change color. And so now this is going to be 3 times minus 2. Be careful here because minus 2 minus 1 is actually going to be minus 3. Okay, so again, what is this? This is all the slopes. What do we want? We want the slope at 2. When do we want it? Now. So this is at minus 3. This is going to be, you can just type this in if you would like. So this is going to be minus 6. Minus 6 times 2 to the negative 3. Which is going to be, this is going to be 8, so this should be negative 3/4. Yeah, okay. So this is going to be negative 0.75. Of course, let's confirm with the calculator. Okay, so take a moment and just enter. Remember, you're entering the original function, okay? So I've already entered it here. There it is. And then let's plot it. Okay, what's happening at 2 anyway? This is interesting because then you can see that at 2 there's going to be some sort of a negative function. So this is already looking good. And so let's go to negative 2. And then now go to function, go to slope. Ta-da! Okay, sorry, I went to negative 2. Why? I don't know, no reason, just being a bit crazy. Okay, so now let's go to slope. There it is. Good, so I'm just going to quickly take a screenshot of that, and so then you can see that indeed this, sometimes it likes to paste on a 5th try instead of the 1st. Why? Nobody knows. Okay, so then at 2, sorry about that, then you can see that at 2, the slope of the tangent is some sort of a negative number, okay? All right, moving on to the intervals of increase and decrease. What's happening here? Okay, so remember that when you have a positive slope, then what we say is we say that this is increasing, and then when you have a negative slope, then we say that this is decreasing. This is some sort of an extremum, okay? This is actually a maximum point, and at maximum, the slope or the derivative is always 0. This is also in your courses, of course, that when the derivative is positive, then you have an increasing function, okay? And when your derivative, so get used to this notation with an apostrophe, is negative, then we say that the function is decreasing. And then when the derivative is 0, then you have some sort of a min or a max, okay? So describe the intervals for which the function is increasing or decreasing. Okay, so here you can see that it is increasing from here to here, okay? So what we would say is when x is greater than -1 or less than 1, it's increasing. The reason that I'm not actually including the equal sign is because here at the actual -1 and 1, it's not increasing or decreasing, it's actually stationary, okay? Similarly, on the decrease, we're going to have two intervals, right? Because it's decreasing here, and it's also decreasing here. All of those derivatives are going to be negative. So when x is less than -1, and when x is greater than 1, then our function is decreasing. Just to finish off the highlighting, you can see this is an increasing, and that will be our increasing thing here. All right, moving on. Using the derivative graph. Okay, here we didn't do any calculus. We just looked, hey, where are things going up and down from left to right? Now we're actually going to be using some calculus for this, okay? Where is this? So somewhere here it is stationary when the function, so what's happening here? This is where it is decreasing. Everywhere here, you're going to have the derivative that's going to be less than 0, okay? So the derivative is less than 0, okay? When it's stationary, then your derivative is going to be equal to 0. And then when it's increasing, then your derivative is going to be greater than 0, okay? That holds always. Just to use the proper notation, then we can write it like this. Less than 0, and here. What does this mean? This is important, because now when they're going to ask us to find the actual stationary points, we're going to take our derivative and we're going to be setting it equal to 0, okay? Yeah, moving on. So this is all summarized here, okay? Now what's happening here? What is this? Well, let's just look. Here we have a negative derivative. So let's have some sort of a stationary point, negative derivative. So we're going to have some sort of a negative slope, shoops, and then 0, and then the slope becomes positive. So that means that when you're switching from it being negative to positive, then you're going to have a minimum. And similarly, what's happening here, you're going from a positive slope to a negative slope, and then over here that's stationary, then this is going to be a maximum, okay? All right, given this function, so this is a nice quadratic, determine the derivative. Okay, well, again, we're just going to use our power rule. Hopefully that's becoming easier. Remember, drop. So this is going to be 2 times 2 is 4, and then the power decreases by 1. Remember, the derivative of 3x is just 3. Remember, we learned that last time, because this becomes 3, this becomes x to the power of 0, which is 1, so that's always gone. And then the minus 5 is just gone, so this is your derivative. Okay, use the derivative. So this is a command for you to not just kind of throw this on the calculator and see where the stationary point is. But what we're going to do is we know that the stationary points are always at the derivative being exactly 0, right? There's no slope, right? The slope here is 0, the slope here is 0. So what we're going to do is you take your derivative and you set it to 0. This will always work. Okay, so we're getting -3/4. Hence, find the range of values. So again, hence means use the previous information. Okay, so we now know that we've stopped at -3/4. We also know that this is a parabola and it's looking up, right? The A is positive, so this is looking something like this. We know here the derivative is 0 at And if you wanted to find the corresponding y, you totally could. But here, basically, where is it increasing? It's increasing here, right? That's your positive slopes. So then we would say that as long as x is bigger than negative 3, 4, then our function is increasing, okay? Positive slope, positive derivative. Moving on. Let's do one more of this. Okay. Given the, okay, so be careful. This is not supposed to have the derivative, okay? This is just supposed to be the function. Sorry about that. Okay, so now the first thing we're going to do is we're going to find the derivative. Okay. And again, remember, pause it. Try it on your own. So 15x squared. Now this is going to be minus 4x. And the constant is always gone. Remember, constant is always a horizontal line, the slope of which is 0. This is kind of the mathematical reasoning of why the derivative disappears. Hence, find where it's stationary. This should sound repetitive a little bit by now. As soon as you hear stationary, you hear that the derivative is equal to 0. Okay, so what we're going to do is we're going to just set this to 0. Okay, we need the roots of this, don't we? Okay, let's go and graph it. Let's go and graph it. Okay, we can zoom in a little bit, but anyway. So what we need is we need the roots. Be careful, so this is 0.267. Good. And then let me just zoom in a bit on this. Okay, so we got the small one, right? This one we got, and now just click next to the other one, and again we need the other root. Okay, it's 0. So when x is 0 and when x is 0.267, then those are our two roots. Okay, what's happening? Is it where is it increasing and where is it decreasing? Okay, so increasing and decreasing. So this is a little bit tricky. You may not like this, but remember what this is. These are derivatives, okay? And what that means is that basically these are all slopes. What that means is that here's, again, you're not looking at the original function. How is this helpful? Since these are all our derivatives, then we can just see when it dips below the x-axis, then these are all going to be negatives. And when it's above the x-axis, all of these are positive slopes, so it's increasing and decreasing. If you don't like that, okay, so this is the derivative graph, you always do have your calculator. So what you could do is you could just graph it, and you could just see what's going on. So let's graph the original. So we're going to have 5x cubed minus 2x squared minus 3. Okay, so this is what the original looks like. This was our first 0. And you can see there's a little dip in there. So what we're having here is we're having a decrease between 0 and 267, whereas here all the slopes are positive. So then here, when x is less than 0, then we're increasing, and when x is greater than 0.267, we're also increasing. Okay. Last one. No, second last one? Okay. The ball is thrown from a cliff. The path of it may be modeled. Determine. Okay, this is the same. This is another way to denote the derivative. So this is going to be drop the 2 down. So this is going to be negative negative 0.1 x plus 1.5, right? And then again, the constant is gone. You can see that this is repetitive. Hence, find the maximum. Again, hence is an important word, okay? It means you have to use your derivative. Again, on a maximum, remember this. On the maximum, the derivative will always be 0. So just take this and set it equal to 0. Take this over, divide. I'll let you do the algebra there. You should be equal to 15. Is this the maximum height? No. This is just the horizontal distance at which it occurs. If you actually want the maximum height, then what we're going to do is we're actually going to substitute this in, right? So go back to the original function and then sub it all in, and you should end up with 93.25. You, of course, can cheat and just put it into the calculator and get the max, but just go through that process of setting the derivative to 0 first. That's what that mark is always looking for. That mark is always looking for you to set the derivative to 0. This is key. Justify that the height is a maximum. Okay, well, what's happening here? We've got 15 and then 93.25. So this is some sort of a negative looking parabola, right? So what you can say is something like the derivative switches from being negative to being positive. Yeah, so this was from being positive, Miss Walsh, to being negative, right? So when it was positive and then it goes into being negative, you can do this with specific values as well. Then what you have is you have a max. All right, last one, almost done. Find the derivative in terms of a. Do not get frightened by this. It's just some number. It can be a 2, a 5, a 7.5, just some constant, okay? So our power rule is going to be posit, find your own. So if this was 5x, this would be 5. If this was 7x, it would be 7. So since it's ax, it's just a, and the 4 is gone. If it has a stationary point, alert, alert, when x is 3, determine the value of x. Okay, stationary point, when you hear stationary point, then what you hear is you hear the derivative is equal to 0. So what that means at 3. So that means that when the derivative at 3 is equal to 0. So that's what we're going to do. We're going to take our expression. So at 3, it's 0. So then you have 6 minus a is equal to 0. Throw the a over and you have 6a. What you could do is you could now that to check, you could you could grab this on your calculator, 6x minus 4, and then just go and see, is there a max or a min when x is equal to 3? Okay, so that's your intervals of increase and decrease. Just remember, if it's increasing, the derivative is positive because all the slopes are positive. And when it's decreasing, then all the derivatives are negative. Goodbye.